Good morning. We start with the second lecture of this course. In the last class, we started talking about atomic bonding and primarily looked at some of the important characteristics of metallic bond, which are listed here. Just to recapitulate, it has low electronic specific heat, it has high electrical conductivity, it is non-directional, strength of this bond is proportional to the number of free electrons per atom, it has high stiffness and there is a relationship between stiffness and bond energy, and it has high melting and boiling point. To recapitulate some of this, we talked about the bond in carbon, and carbon has half filled outer orbit. As it was said, if the orbit is half full, so that means there are 4 electrons in the outer orbit, all have parallel spin. In this case, we call this orbit as a hybridized orbit, and all 4 electrons in this orbit have identical energy. So, therefore, if you try to arrange this in solid, these bonds will be subtending equal angle. So, 4 equal angle. The only way you can have this is like put it at the center of a cube. In that case, the other nearest atom will be located either here, 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 here. So, of that, with that atom, it will form a bond with one having just opposite this spin. So, this atom will have the spin here, rest they are similar. And I asked you to find out this angle, and I hope you have done. If not, I think when we do little more detail the crystal structure, it will be evident. You can solve this by trigonometry, simple trigonometry, place an atom point at the center of a tetrahedron, regular tetrahedron, and join the center to the corner, this corner, and then try to find out this angle. Now, this type of bond is highly directional. It has a completely filled up valency band. So, therefore, there is no electron to carry charge. Therefore, it is insulator, it has insulating property, and this bonding is extremely strong. The distance between carbon to carbon atom is very less. So, therefore, it has high modulus. So, this is the structure you get in diamond. Next, we looked at the nature of that bond strength, the origin of the bond strength. So, when you have 2 atoms, you can visualize that this atom and this atom as if they are held by a spring. If you try to displace it a little, it will try to come back, but the spring is also very steep. If you try to push it too close, it will try to repel. And this is, so that is why you have 2 kind of force. One is a force of attraction, another is a force of repulsion. I wanted you to show by differentiating the position or distance r at which this energy is bonding, this energy u is minimum. And I hope you have done. If not, the steps are shown. If you differentiate, you will find and equate it to 0, you find. So, this is the equilibrium distance. This expression gives you the equilibrium distance, and usually look at this exponent m and n. Now, this is the attraction force. Now, in case of electrostatic bond or ionic bond, this m is 1, and m is usually rather m is always less than n. So, that means when the atoms are nearby, this is much more dominant than the repulsive force. Now, in case of a van der Waals bond which is weaker, there the index m is equal to 6. Now, lower the value of m indicates that the bond is stronger. Now, once you have found out this, if you substitute this R naught in this expression, you will get the expression for the minimum bond energy. And a reference was made that this bond energy will have a direct relationship with the strength of the material. Now, and to find out the relationship between bond energy and stiffness, you imagine that you have two atoms which are nearby, its equilibrium distance between this and this is r naught. You try to displace it by a small distance x, and then the value of that energy u near r naught, that means at r naught plus x, can be given by a Taylor series. So, this is the value of u at r naught, then the first differential at r naught times distance x, then second differential, then x square times x square. There is a constant coefficient 1 over 2, and we can neglect that higher order term which is smaller. Now, from this you can see the change in energy, you can rewrite this in this form, and this we know that when u is minimum, that is at r naught, this is equal to 0. So, therefore, this does not remain in this. And now, if you differentiate this with a distance, then you get force. Then obviously, you get this term, the second differential d 2 u dr square at r equal to r naught times x, and this is known as second differential, can be defined as stiffness. So, therefore, stiffness, relationship between stiffness and u is given by this, and I wanted you to go through and this and derive an expression or relationship between bond strength and bond strength or bond energy and stiffness. Now, we are very familiar with Young's modulus. Now, how do you, is there a relationship between Young's modulus and stiffness? So, visualize two atoms in the same way, separated by a distance r naught, you try to displace it by a distance, small distance x. Then the force that is acting between the two, the restoring force or that pull that which you are applying, this is stiffness time x. So, and this and stress we know is defined as force over area. Assume that this area of the cross section area of this atom is proportional to r naught square. So, F over r naught square is the stress, and therefore, you substitute here, and now we know that x, which is the displacement, x is the displacement and R naught is the original distance between the two atoms. So, this is equal to strain. So, now we have a relationship between stress and strain. Now, we know the stress and strain, the relation that there is a proportionality constant and which is known as Young's modulus. So, therefore, what we can say that Young's modulus is S over R naught. Now, if you differentiate this bond energy, this is the first differential, differentiate it second time, you get this, and substitute that R naught, the value of R naught over here. In that case, what you get is d 2 u dr square at R equal to R naught. In that case, this is the value, and then you try and find out that Young's modulus. Young's modulus will be S over R naught. So, again you substitute this over here, you get this. So, there is a direct relationship between Young's modulus and the bond energy, or that coefficient which is defined by these four constant A, B and 2 index M and N. If you look at this bond energy versus stiffness, here are some examples which we have listed. It is a covalent bond, the carbon carbon. In fact, the diamond is the strongest material. For this, the Young's modulus is of the order of 1000 GPa. And from this, if you know this atomic distance, you just multiply this by the atomic distance, you get the stiffness. So, basically this atomic distance, roughly it is of the order of 1 to 2 angstrom, between 1 to 2 angstrom, it could be 1.5, or let us say that it is 2 angstrom or 20 nanometer. So, 10 to the power minus 9. So, if you multiply, this is GPa. So, that means this is 10 to the power 3 the gigapascal, it is 10 to the power 9. So, you will get that this may come around 200. So, same is true in all other cases also. So, here are the Young's modulus for few metallic bonds, which is of the order of 300 GPa, whereas the Young's Young's modulus is of this order, and then bond strength is this. Now, in ionic crystal like alumina, the values are this. So, simply you multiply this by the interatomic spacing, the nearest interatomic spacing, you get the stiffness. Now, if you look at the bond between these polymers, this is the Young's modulus and this is the stiffness. Now, here it is stiffness is very low, and it is primarily, if you look at the carbon carbon bond, which is very strong, the carbon carbon bond, but in polymer, you know, along the chain it has high strength, but its strength is primarily determined by van der Waals bonds, which are between chains. So, it will be several chains. So, between chain there is a van der Waals bond. So, its strength here, here and here is primarily determined by van der Waals bond. Now, we also looked at specific heat. We also looked at specific heat of metal, and where we came to know that classical mechanics cannot explain why specific heat becomes 0 at 0 degree Kelvin. It can, that classical mechanics can explain the Dulong-Petit law. So, that means over here at a higher temperature or room temperature, or normally metals room temperature is considered to be quite high for most metallic materials. So, here most metallic material have a specific heat, molar specific heat around 6 calorie per gram mole per degree Kelvin. So, it can explain that, but when you go to a lower temperature, it gradually goes down to 0. And we talked about that to explain this, one has to refer to quantum mechanics. And quantum mechanics, basically here is a table, short table, which gives you when do you apply quantum mechanics and when classical mechanics. Usually when we were looking at high temperature and high energy, that means particles have higher energy, it is classical mechanics gives correct prediction. However, when the temperature becomes very low, or energy of particles are also very low, in that case classical mechanics gives wrong prediction, and this is where one need to apply the principle of quantum mechanics. And usually the calculations using quantum mechanics are little difficult to understand and little complex. So, therefore, in normal cases we do not, if the temperature is high and energy of the particles they are also high, it is use of it is not required. Now, quantum mechanics imposes certain restrictions on occupancy and transition of particles from one energy level to another, and this is given by this statistics. The probability of occupation probability of a particular orbit being occupied or filled up is given by a statistics called Fermi-Dirac statistics, in contrast to Maxwell-Boltzmann statistics, which is applicable in case of classical mechanics. And the difference between the two is shown in this diagram. This is the probability that an energy level E I is occupied. 1 means it is fully occupied, 0 means it is vacant, and at absolute 0 the Fermi-Dirac distribution will look like this. So, beyond an energy level, say E naught, which is called Fermi energy, there is no electron in the band, whereas at higher temperature distribution will be something like this. So, at Fermi level you can say half the number of electrons occupy energy less than the Fermi level and half beyond the Fermi level. So, this part of the diagram, the probability distribution, is very similar to that of the Maxwell-Boltzmann distribution. So, that is why at higher temperature both predictions are similar. Now, to calculate specific heat using quantum mechanics based model, one thinks of atoms which are arranged in a periodic fashion in a crystal, as if they are connected by spring, and these atoms they keep on oscillating about its mean position of rest. and this oscillation, that frequency, is a function of temperature. Now, in terms of in quantum mechanical model, it is assumed that this oscillator can have certain specified level of energy, which is given by this. This is Planck's constant, this is the frequency, this is a quantum number, n plus half. So, one point which obviously comes up, that n is an integer, it can have 0, 1, 2. So, therefore, even when n is 0, so that is at 0 degree Kelvin, it can have electrons will have small, but some finite energy. So, there is a basic difference between this and classical mechanics. Using this, Einstein worked out, this was the first quantum mechanics based approach to explain molar specific heat, and he came out with an expression which says that molar specific heat will decrease exponentially. Around the same time, a little later, the Debye came up with another model which predicted that molar specific heat is proportional to T to the power 3, and he introduced both Einstein here also, this theta is called Debye characteristic temperature, and above this characteristic temperature, that molar specific heat obtained from classical mechanics and quantum mechanics, they are same. And at low temperature, the Debye prediction is closer to the experimentally determined values. And this, I think, we went through. If we apply this to free electron, that means to apply this to find out what is the contribution of electrons, that free electrons in an atom, to the specific heat. If you go through this calculation which was explained in the last class, you will find out that if you follow classical mechanics, that means all electrons can absorb thermal energy, then that electronic contribution, it comes out to be very large. But if you apply quantum mechanics, only the electron near the Fermi energy can absorb energy. So, therefore, the number of electrons which can absorb thermal energy is 2 kT over Fermi energy, and if you calculate this, it will come out to be very small, maybe about 1% at room temperature. So, therefore, electronic contribution to specific heat is very negligible in compared to the atomic contribution of atomic vibration to specific heat. So, with this brief recollection of what was covered in the last class, let us look at how do we explain that electrical conductivity of metallic material, and what are the factors that determines electrical conductivity. The electrons are the charge carrier in metal, and when you apply an electric field, if there will be a force acting on the electron, which is given by this expression. Now, we know the mass of electron is m. So, if you divide this force by mass, you get acceleration. Now, to calculate this average velocity, so imagine these electrons which are moving in all directions, it can move in different directions until it meets an obstacle and its direction changes. So, basically what we can say that what is the relaxation time or the time between this an electron hitting an obstruction. If we say that this time is t, then we multiply acceleration by time, we get average velocity. Then the current flux, it is possible to calculate, that is current flux J will be proportional to the number of electrons n, electronic charge and then average velocity. And here if you substitute that average velocity over here, you get this term. Now, J is proportional to, this expression says that J is proportional to the electrical field. This is one way of specifying Ohm's law, and that constant of proportionality is sigma, which is known as conductivity. So, this is the expression for conductivity. So, it depends primarily on the number of charge carrier, E is constant, and the relaxation time T. Now, with this background, let us try and estimate what is the likely time or an idea about the time scale for this relaxation time T. Now, this is the expression for relaxation time. See, 1 over this rho is the resistivity. So, rho is basically resistivity, which is 1 over conductivity. So, for metals this is known. Take a case of, say, let us say gold, for which this resistivity is given by 2.2 into 10 to the power minus 8 ohm meter. Now, this is a constant charge of an electron which is known. What you need to calculate here is n, because m is also constant, this is known. And how do you calculate that number of electrons which take part in conductivity or in conducting electricity? Now, one way could be, if you can you find it out from density. Density of a metal is known. Say suppose this density of gold is D, which is given as around 19 gram per cc. If you divide this by its atomic weight, so you get the mass of one atomic mass of 1 cc of gold, and then you multiply it by the Avogadro number. So, then you get n number per cc, and you need to convert it into meter cube to substitute in this expression. So, one need to be careful about the units. You should substitute all these constants or the values in consistent unit. Once you do this, you get a value of around 2.74 into 10 to the power minus 14 second. Now, let us try and find out what is the drift velocity. It is possible to calculate drift velocity from, it is related to Fermi energy E naught. In fact, if you look at that Fermi energy, here the entire energy is due to the kinetic energy of electron, and this is equal to half mass of electron into velocity square. So, from here it is possible to estimate the drift velocity. This is of the order of 10 to the power 8 centimeter per second. So, therefore, mean free path of this electron is, if you multiply this and this, you get, this is of the order of 10 to the power minus 6 centimeter. So, therefore, you can say that atomic distance for most crystalline structure is of the order of 2 angstrom. So, angstrom means it is 10 to the power minus 8 centimeter. So, therefore, this mean free path is around, this is 2 order of magnitude higher than this. So, you can say that mean free path of this electron is around 100 times atomic spacing. So, therefore, in metals are good conductor, whereas covalent bonds you do not have free electrons. So, therefore, they are insulator. Now, let us look at the conductivity in little more detail. So, effect of temperature on conductivity. Now, this conductivity expression is written like this. So, now there are which are the terms which are affected by temperature. This is the drift velocity. Now, drift velocity, it is determined by Fermi energy, but this Fermi energy is a very weak function of temperature. So, therefore, you cannot change much. So, this is ruled out. So, therefore, and here also this number of electron, it is determined by the crystal structure or atomic structure. This is constant. So, the only term which can change primarily is L. So, this is the mean free path can change. Now, this mean free path is proportional to temperature. Due to scattering, these electrons are scattered by, because you can assume that a crystal is made up of periodic arrangement of atoms. Atoms are placed at certain mean position of rest. They are not stationary, they keep vibrating, and this extent of vibration increases with temperature. So, that means there is a little loss in periodicity, and this vibrating atoms, they will emit particles called phonon. That vibration energy, you can say it is emitted by the oscillating atoms as phonons, and these phonons and electron, that there will be interactions and this electron gets scattered. If there are too many phonons emitted, this extent of scattering will be high. So, therefore, at a higher temperature, higher the temperature, there will be more atomic vibration, there will be more scattering. So, therefore, you can say that mean free path is proportional to temperature, and resistivity is inversely proportional to temperature. So, therefore, resistivity is proportional to temperature. So, most metals, the resistivity increases with temperature, and this linear dependence at a high, except at a very low temperature, it deviates from linearity, but by and large resistivity is a linear function of temperature. Therefore, resistance of metallic wires are often used as a temperature measuring device. Now, electrons can also get scattered by impurities. If there are different atoms present which disturbs the periodic nature and the crystal structure, they also will contribute to scattering. Like when you do alloying, you put in a second element in the lattice, and they can be treated as impurity, because its characteristic is different from the atoms of which the main metal, that structure is made up of. So, therefore, they also will be a source of, they also will scatter electrons. So, therefore, if you increase this impurity, there should be a direct relationship between resistivity and the concentration of these impurity elements, which is represented like this. Rho is proportional to the atom fraction of that impurity. Now, you can say, suppose we take a binary system, say two element A and B both are conductor and they can be mixed in all proportion. So, both end and this end also the resistivity will go up with concentration, this end also, this is the base resistivity of metal B. So, this also will go up, and if you plot the total, you will get a maxima somewhere in between, where x is 0.5. So, logically in such cases effect of impurity or effect of alloying can be put by a factor like this, x is rho is proportional to x into 1 minus x. So, any alloy will have poorer conductivity. There is a lot of similarity between thermal conductivity and electrical conductivity. It may be interesting to look at this. So, now electrons are the primary carrier of electricity in metals. Now, if you look at the thermal conductivity, this thermal conductivity will depend primarily on two factors. One is its specific heat. Now, this specific heat is actually primarily controlled by the atomic vibrations. And apart from that, you have these atomic vibrations, you can say they are emitted as phonons, and phonons, the displacement of these phonons, these wavelengths so let us look at this. Specific heat will be a function of this thermal conductivity will be a function of specific heat, and the mean free path of electron and mean free path of photon. Now, mean free path of electron we have just seen is of the order of 100 atomic spacing, whereas mean free path of phonon. So, these wavelengths are much smaller. So, they get scattered very easily, and this is of the order of atomic spacing. So, therefore, any crystal structure or any structure, solid or liquid, wherever you have basically the ionic or covalent bond, there is no free electron. So, they are bad conductors, in fact, even bad thermal conductor. Metals have free electrons, they are good electrical conductor. So, they are good thermal conductor as well. Now, here also you can discuss in the same way what will be the effect of temperature. With increasing temperature, resistivity goes up. So, also thermal conductivity will go down. Similarly, alloy addition also will bring down thermal conductivity. Now, because it will be interesting to see what is the relationship between thermal conductivity and electrical conductivity, because both the cases electron is the charge carrier. In fact, if you look at thermal conductivity and electrical conductivity for most metal, we will find that this is a constant, and this constant is known as Widman-Franch constant, and this magnitude is given here. Now, with this we have covered the nature of atomic bond. Now, let us look at the crystal structure. Metals, all metals, they are crystalline. Now, crystalline material, the atoms are arranged in a periodic fashion. Now, how do we represent this periodicity or how do we visualize this periodic arrangement of atoms in a crystal? In order to do that, we make use of a framework, an array of point in space. Now, we visualize the array in such a way that each of these points have identical surrounding, and this array of point is in space is known as lattice. Now, let us try and look at how does this point lattice look like. Now, suppose we consider one this particular figure consisting of 4 points here, 4 points here, and try to repeat this in this direction as well as this direction. So, something like this. So, that means one point has a surrounding, it has atoms, say one here, one here, one here, one here, one here, one here. So, this has a surrounding of 6 points, and if you repeat this, it is possible to generate a lattice of points like this, and this is called point lattice, and the smallest building block, this is known as unit cell. Now, all crystal structures we try to represent in terms of this lattice structure. Now, this is the lattice this is the lattice structure. Now, when you have points, this is the smallest building block of that lattice called unit cell, and let us look at this particular unit cell. We call here we have points only at the corner of the cell. And let us try to calculate there are how many lattice point in a cell like this. This cell where you have points only at the corner is called primitive cell. And let us try and calculate what is the number of points in this primitive cell. Now, here if you go back to the previous is what you have, this particular point does not solely belong to one unit cell, it is shared by all the adjacent unit cell. Now, here how many adjacent unit cells are there to this point? You have 1 here, 2 here, 3, similarly another here, 4, 4 this side, similarly 4 on this side as well. So, this point is shared by 8 unit cells, nearby unit cell. So, therefore, you can say that this primitive cell contains that number of points is, it has 8 corners, but each corner point is shared by 8 such neighboring unit cell. So, contribution of this each is 1/8. So, this is 1. Now, you can also have unit cell. It is not necessary that unit cell should have points only at the corner. They can have certain additional points as well, which is shown here. So, this is the primitive cell. Here this number is 1. If you have 1 at the center of the body, in that case that number of points per unit cell will be 2, because this corner contribution of corner is 1 and this central point exclusively belongs to this unit cell. So, it is not a part of any neighboring cell. So, therefore, here the number of points per unit cell is 2. Similarly, this is called body centered unit cell, this is primitive cell, this is called face centered. So, in addition to the corner points, you have points at the each of the face centered. By substituting this additional point, we do not violate the definition of a point lattice, because point lattice we defined that a point lattice is an array of point in space. So, that every point has identical surrounding. I think you can take this as an exercise and try to point out or plot the array or arrangement of neighboring points to a body centered unit cell and a face centered unit cell. And you also try to find out in a face centered unit cell what is the number of points per unit cell. Now, let us look at the unit cell little more critically. How do you define this unit cell, which is shown in this slide? Say this is a unit cell. It is defined by its linear dimension, dimension of each of these edges. Say suppose this is a set of axes x, y, z. Very often we normally represent in geometry the axis as x, y, z. In crystallography, we try to represent them as a, b, c. So, for x we put it x. So, the distance between 2 points along this direction is represented as a vector a. Similarly, the distance between 2 points along axis y is put as b, and the distance between 2 points along the z direction is c. Similarly, apart from this 3 linear dimension, we also need to define angle between these axes. So, this angle just opposite a. So, this is x axis, or in crystallography we call it a. So, opposite a, so this we call alpha. Similarly, the angle opposite y we call this beta, and the angle opposite z we call gamma. Now, depending on the magnitudes or the relationship between this linear dimension a, b, c and this angle alpha, beta, gamma, you can have different shapes for this unit cell, and which is listed here, and based on this we can classify all crystals into 7 classes, which is listed here. Say in cubic, and for most metallic material the crystal structure can be described by cubic, or most of the cases, as we will come to know, the crystal structure is cubic. Here all the lattice a equal to b equal to c, and the 3 angles alpha, beta, gamma, they are equal and equal to 90 degree. This is the most symmetric crystal that we can think of, and down this as you go, that element of symmetry goes on decreasing, and you have the other extreme triclinic, where none of these parameter a, b, c, they are equal, and none of these angles are equal, alpha, beta, gamma, they are different, and this is called triclinic. So, this is the this has the highest symmetry, this has the least symmetry. And intermediate, you have tetragonal, hexagonal, orthorhombic, rhombohedral and monoclinic, and the relationship between the A, B, C and alpha, beta, gamma are listed here, and these values they are called lattice parameter. So, A, B, C and alpha, beta, gamma, they are called lattice parameter. Now, most of the metallic crystals, they belong to one of these, not that there are no other crystal structure, but primarily this is body centered cubic, this is face centered cubic, and this structure, although it is primitive lattice is hexagonal, we call this hexagonal close packed structure. Now, it will be good to look at what is the number of nearest neighbor, say like in case of a BCC lattice. So, look at this, and the number of nearest neighbor is 1, 2, 3, 4 on the top, 4 at the bottom. So, here we call this number of nearest neighbor as a coordination number, and this is 8. And from this it is little difficult to find out the coordination number. We will try and look at it little later, but here it is easy, relatively easy. You take this and try to find out the number of nearest neighbor. So, let us say you take this, you have 6 in the plane, you have 3 neighbors here, this here, similarly you have 1 over here, 1, 2, 3 and similarly 3 at the top. So, in this case coordination number is 12. So, this is the maximum coordination number you can have in a crystal structure, and in this case metals. So, one of the simplest way we can visualize this atom, we can assume them to be hard sphere and go through few calculation, hard sphere model and go through a few calculations. You try to find out, this is a little elaborate view of that face centered cubic structure, assuming they are hard sphere. Along this directions they touch each other. So, if you assume the radius of the atom to be r, then try and find out what is the relationship between r and the lattice parameter, that is, this is the lattice parameter A. So, what is the relationship between the atom radius and A, say for FCC, and try to find this for BCC. And another thing, it will be interesting to look at this the array little more carefully. If you look at that atomic array, they are arranged like this. This is a hard sphere, surrounding it you have 6 atoms. Suppose we call this layer A. Now, on that if you try to bring another layer of hard sphere, so where does it go? There are 2 places here. Say if I go to the previous, here there are 2 places next layer can occupy. So, one is here, another here, but if you put an atom here, part of this gets blocked. So, you can only have either here or here. So, here it comes, it occupies one of the position, we call this layer B, and then we bring in another to the other side. We call this as a layer C. So, look at this arrangement from this side, it has a similarity to face centered cubic structure. So, you try and visualize the same thing in an hexagonal, which is shown over here. You have one layer, we call this A, second layer, and the third layer, second layer is B, and the third layer it goes and occupy layer A, there is no C layer, and you try and visualize this. This resembles hexagonal closed back structure. With this, we finish the second lecture on atomic bond and crystal structure. You can go through those exercises, particularly assuming atomic bond, and apart from calculating the relationship between the radius of the atom and lattice parameter, you try to find out lattice parameter from density of a metal. And next class, we will talk about a little bit more detail, how do we represent the directions and planes in a crystal, introduce the concept of Miller indices, and we will talk a little about stereographic projection. Thank you.